Welcome to this tutorial on scale.product attention in Pytorch. Today we're going to explore one of the most fundamental building blocks of transformer models. We'll start by understanding what scale.product attention is, then master the torch.nn.functional.scaled_dot_product_attention API. We'll also learn how to apply attention masks and causal masking, explore advanced features like dropout and grouped query attention, and finally build practical applications using these attention mechanisms. Let's begin with an architecture overview. The scale.product attention is truly the foundation of transformer models. It works by computing attention weights between queries and keys, and then uses these weights to create a weighted combination of values. Take a look at this diagram, which shows how the attention mechanism flows from inputs through the computation process. First, let me set up our environment with all the necessary imports. We'll need Torch and its functional API, along with some utilities for visualization. Now, let's dive into the simplest possible example to understand how attention works at its core. Here's our first hands-on example. I'm creating the simplest possible attention setup with a single batch, 4 positions in our sequence, and an embedding dimension of 8. We create 3 tensors, query, key, and value, all with random values. Then we apply the scale.product attention function. Notice how the output maintains the same shape as our input query tensor. Perfect. We can see that our input shapes for Q, K, and V are all batch size 1, sequence length 4, and embedding dimension 8. The output maintains exactly the same shape, which is what we expect from the attention mechanism. Now let me explain the mathematics behind scale.product attention. The formula computes a weighted sum of values V based on the similarity between queries Q and keys K. The key insight is that we compute QK transpose to get attention scores, then scale by 1 over square root of dk to prevent gradient vanishing, apply softmax to normalize, and finally multiply by V. The scaling factor is crucial because without it, large dot products would push softmax into regions with extremely small gradients, making training difficult. Let's implement the attention mechanism manually to really understand what's happening under the hood. I'll create a function that computes each step explicitly. First, we get the dimension and calculate our scale factor as 1 over square root of dk, then we compute attention scores by multiplying query with key transpose. We scale these scores, apply softmax to get normalized attention weights, and finally apply these weights to our values. Let me verify that our manual implementation matches Pytorch's built-in function. Excellent, our manual and built-in implementations match perfectly. This confirms that we understand exactly what the scale.product attention is doing internally. Now let's visualize how attention weights distribute across positions to get an intuitive understanding of what's happening. Here I'm creating a visualization function that will show us the attention weights as a heat map. This helps us see which positions are attending to which other positions. Looking at this heat map, we can see the attention pattern from our basic example. Each row represents a query position, and each column represents a key position. The values show how much attention each query pays to each key. Notice how the attention weights in each row sum to 1, thanks to the softmax normalization. Let me show you a comprehensive parameter documentation table. Each parameter has a specific purpose in controlling the attention mechanism. The query, key, and value tensors are required inputs. The attention mask lets us control which positions can attend to each other. Dropout provides regularization during training. The is_causal flag enables causal masking for autoregressive models. The scale parameter controls attention sharpness, and enable_GQA allows for grouped query attention, which we'll explore later. Now let's look at multi-head attention, which is how transformers actually use attention in practice. Real transformers use multiple attention heads to capture different types of relationships simultaneously. Here's a multi-head attention example. I'm creating tensors with 2 batches, 8 attention heads, sequence length of 16, and head dimension of 64. Notice how the tensor now has an additional dimension for the heads. Each head can learn to attend to different aspects of the input. When we apply the attention function, it processes all heads in parallel. Great, we can see our multi-head attention is working correctly. With 8 heads, each with dimension 64, we're able to capture 8 different attention patterns simultaneously. The output maintains the same shape as our input, which is exactly what we need. Let's explore attention masks, which give us fine-grained control over which positions can attend to each other. Pytorch supports both Boolean and float masks, and I'll show you how both work. I'm demonstrating both Boolean and float masks here. With Boolean masks, true means the position can attend, while false means it's masked out. For float masks, we use additive masking where large negative values, like -10⁹, effectively zero out attention weights after softmax. In this example, I'm masking out the last 2 positions so they can't be attended to. Perfect. Both Boolean and float masks are working correctly without any NaN values. This gives us flexibility in how we want to implement masking in our models. Now let me visualize how masking affects the attention pattern by comparing attention weights with and without masks. Look at the difference between these 2 heat maps. On the left, without masking, attention flows freely between all positions. On the right, with positions 3 and beyond masked, you can see those columns have near 0 attention weights. The remaining attention redistributes among the unmasked positions, and each row still sums to 1. Causal attention is crucial for autoregressive models like GPT. In causal attention, each position can only attend to previous positions, not future ones. This prevents information leakage from the future during training. Take a look at this diagram showing the causal mask pattern. Let me demonstrate causal attention in action. I'll create a test to verify that causality is properly enforced. We apply causal attention, then dramatically change the last position's value. If causal attention works correctly, this change shouldn't affect any previous positions, only the last one. Excellent, causal attention is working perfectly. We can see that past positions have exactly 0 difference when we change future values, while the last position shows a large difference of about 38.84. This confirms that information correctly flows only from past to future, never backwards. Let's visualize the causal attention pattern to see the characteristic lower triangular structure. Here's the classic causal attention pattern. Notice the lower triangular structure where each query position can only attend to keys at the same position or earlier. The upper triangle is completely masked out, shown in white. This pattern ensures that during generation, each token only has access to previously generated tokens. Dropout is an important regularization technique that can be applied to attention weights during training. Let's see how it affects the output variance. I'm testing different dropout rates from 0 to 0.7 and measuring how they affect output variance. With no dropout, the output is deterministic. As we increase dropout probability, we randomly zero out attention weights, which increases the variance of our outputs. This randomness helps prevent overfitting during training. As expected, we can see a clear trend. With no dropout, variance is 0 since the output is deterministic. As dropout increases to 0.7, the variance jumps to about 0.46. This increasing variance with higher dropout rates is exactly what we want for regularization during training. Let me create a visualization showing how dropout affects output variance across different rates. This graph clearly shows the relationship between dropout probability and output variance. The variance increases roughly quadratically with dropout rate. In practice, dropout values between 0.1 and 0.3 are commonly used for attention layers, providing a good balance between regularization and stability. The scale parameter gives us control over the sharpness of attention distributions. Let's explore how different scale factors affect attention patterns. I'm testing different scale factors to see their effect on attention entropy. The default scale is 1 over square root of 64, which equals 0.125. Smaller scales create softer, more uniform attention, while larger scales create sharper, more focused attention. Entropy measures how spread out the attention is, with higher entropy meaning more uniform distribution. We can see how scale dramatically affects attention focus. With a small scale of 0.05, we get high entropy of about 2.01, meaning attention is spread out. The default scale of 0.125 gives moderate entropy. As we increase the scale to 1, entropy drops to just 0.26, indicating very focused attention on just a few positions. Let's visualize how different scale factors affect the actual attention distribution patterns. These heat maps beautifully illustrate the effect of scale. On the left with small scale, attention weights are distributed fairly evenly. In the middle with default scale, we see moderate focus. On the right with large scale, attention becomes very sharp, with most weight concentrated on just 1 or 2 positions. This is why it's called attention sharpness. Now let's explore grouped query attention, or GQA, which is an important optimization technique used in models like Llama 2. GQA uses fewer key and value heads than query heads, significantly reducing memory usage and computation. Here's a GQA example with 8 query heads, but only 2 key value heads. This means each key value head serves 4 query heads. The key insight is that we can share key and value computations across multiple query heads without significantly impacting model quality. This configuration gives us 75% memory savings for key value storage. Perfect! Our GQA configuration is working correctly. We have 8 query heads sharing just 2 sets of keys and values with a group size of 4. This results in 75% memory savings for KV storage, which becomes crucial when dealing with long sequences or large batch sizes. The output still has 8 heads, maintaining the model's expressiveness. Let me visualize the memory savings and head distribution comparing standard multi-head attention with grouped query attention. These charts clearly show the efficiency gains from GQA. On the left, we see the dramatic reduction in memory usage, about 50% overall. On the right, you can see how standard attention uses equal numbers of query and key value heads, while GQA uses far fewer key value heads. With a group size of 4, we're getting substantial memory savings of 50% overall while maintaining model quality. Cross-attention is used when queries and keys or values have different sequence lengths, which is common in encoder-decoder models like machine translation systems. In this cross-attention example, I have queries with length 10, representing a decoder, and keys and values with length 20, representing an encoder. Each of the 10 query positions can attend to all 20 key positions, creating a 10 by 20 attention matrix. The output follows the query length, giving us 10 positions as output. Excellent! Our cross-attention is working correctly. We can see that with query length 10 and key value length 20, each query position attends to all 20 encoder positions. This is exactly how encoder-decoder models work, where the decoder attends to the full encoder output to generate translations or other sequence-to-sequence outputs. Let's visualize a cross-attention pattern to see how decoder positions attend to encoder positions. This cross-attention heat map shows how 6 decoder positions attend to 10 encoder positions. Each row represents a decoder query, and each column represents an encoder key. The rectangular shape, rather than square, is characteristic of cross-attention. Each decoder position can see and attend to all encoder positions, allowing it to gather relevant information from the entire input sequence. Now let's build a practical application that demonstrates attention in action for a real sequence modeling task. I'm creating a simple attention-based model that shows how to use scaled dot product attention in practice. This model has an embedding layer, linear projections for queries, keys, and values, and uses multi-head attention. The forward method embeds the input, projects to QKV, reshapes for multi-head attention, applies our scaled dot product attention function with causal masking, and then projects to vocabulary logits. This is essentially a simplified transformer decoder layer. Our model is working perfectly. With vocabulary size 100, embedding dimension 64, and 8 attention heads, we've successfully created a working attention-based model. The input shape shows we're processing 4 batches of sequences with length 16, and the output gives us logits over the entire vocabulary for each position. This demonstrates how scaled dot product attention fits into a real model architecture. Let's discuss performance considerations. Pytorch's scaled dot product attention automatically selects the best backend implementation based on your hardware and input characteristics, whether that's flash attention, memory-efficient attention, or the standard math implementation. I'm running performance benchmarks with different input sizes to show how attention scales. We test small, medium, and large configurations, measuring average time per forward pass and calculating throughput in sequences per second. The function includes warm-up iterations to ensure consistent measurements. These benchmarks show how attention performance scales with input size. The small configuration processes nearly 500,000 sequences per second. The medium configuration still maintains over 600,000 sequences per second despite larger inputs. The large configuration with sequence length 512 drops to about 290,000 sequences per second, showing the quadratic complexity of attention. Remember, actual performance depends heavily on your specific hardware and which backend Pytorch selects. Now let's cover common pitfalls and best practices when using scaled dot product attention. Let me demonstrate two common pitfalls. First, you cannot use both is_causal and an attention mask together as they conflict. Second, I'll show the valid mask shapes and how broadcasting works. Masks can be provided at different dimensions, and Pytorch will broadcast them appropriately. Good, we've verified two important points. First, Pytorch correctly prevents using both is_causal and attention mask together, avoiding potential conflicts. Second, mask broadcasting is flexible, accepting masks of shape L by S, 1 by L by S, B by 1 by L by S, or the full B by H by L by S. This flexibility makes it easy to apply the same mask across batches or heads when needed. Let me summarize the best practices for using scaled dot product attention. Use GQA when you need to reduce memory in large models. The built-in function handles numerical stability better than manual implementations. Remember to set dropout to 0 during evaluation. Let Pytorch choose the optimal backend automatically. Use Boolean masks for binary decisions and float masks for score adjustments. For autoregressive models, use is_causal equals true instead of manual masking. And the default scale of 1 over square root dk works well for most cases. Finally, let's create a comprehensive example that combines multiple attention features together. I'll use grouped query attention with 8 query heads and 2 key value heads, apply causal masking for autoregressive behavior, add dropout for regularization, and use a custom scale factor. This demonstrates how all these features work together seamlessly. Excellent! Our comprehensive example successfully combines all the advanced features we've learned. We're using grouped query attention with an 8:2 ratio, causal masking, 10% dropout, and a custom scale of 0.2. The output statistics show reasonable values with mean near 0 and standard deviation around 0.6. This demonstrates that all these features, GQA, causal masking, dropout, and custom scaling, work together harmoniously in the scaled dot product attention function.